And next, we'll have a contributed talk from Jordan Lay from the New York University on choice and deliberation in a strategic planning game in monkeys. Working on the mic.
Can people hear me in the back? Yeah, give me a little wave. Hi. Cool. So yeah, I'm very excited to talk about some ongoing work that we have in collaboration with the Lee Lab at Johns Hopkins University and my lab at NYU, of which I am a part. But let me start with the obvious. Planning is hard. And even though this talk is going to be primarily about non-human primates, I should point out that planning is also hard for non-human primates. Maybe especially hard for some of us. Yes, that is an actual text from me to an actual group chat. I am in a planning lab and I can't I can't plan my own presentation. Don't come at me. And more evidence of my inability to plan, that's me preparing the slides at the airport, and that's me emailing Roshan like literally yesterday, panicking about this presentation. But planning is also interesting for a variety of other reasons, particularly with its new rise in interest in machine learning. If we look at examples like AlphaGo, AlphaZero, OpenAI 5, and particularly with this new rise of agentic models, which sort of aim to combine the distributed learning capabilities of LLMs, as well as the structured and more complex reasoning capabilities of reinforcement learning. So why all the fuss about planning? Well, at least personally, I think that it has to do with the difficulty of planning, particularly the ability to think ahead multiple steps into the future, encounter and plan for states that you may never have encountered in the past. And also, it requires us to sort of form abstract representations of our environment and features of that environment. And thankfully, reinforcement learning has a lot to say both about planning and artificial agents as well as biological agents, particularly through the lens of model-based and model-free learning. In model-free learning, you can think of an agent interacting with its environment through basically being a glorified filing cabinet. Every single time it gets an example, it files that example away and then tries to pattern match based on that example to decide what the best action is over time. Versus that's in contrast to model-based planning, where in model-based planning, the idea is that you form a simulation of your environment. And based on that simulation, you get to choose what your favorite action would be. Now, thankfully in neuroscience, there's been this huge push to connect different areas of the brain to different modes of learning, particularly the prefrontal cortex being involved in things like representing state action outcomes, perhaps arbitrating between different strategies. A lot of different studies showing different areas of the PFC, particularly DMPFC, DLPFC, VNPFC, and others as being implicated in sort of these kind of model-based reasoning tasks. But also, if we look at the striatum, we also see examples of studies, particularly showing that the dopaminergic system in the brain is also involved in encoding model-based value, model-free value, so on and so forth. And of course, there's this sort of I don't know, canonical or like, I guess, almost pop science idea that maybe the striatum encodes the model-free and the PFC encodes the model-based. But more recently, there's been a lot of evidence sort of putting that into question, particularly with a lot of new theoretical approaches suggesting that the PFC might be doing something like being an actor, striatum might be a critic, PFC and striatum might act as a meta-reinforcement learning system, or they might be embedded in some larger system that also works with its environment and learns with memory and so on. Now, today, I'm not going to make a hard claim about these theoretical implications, but all I want to do is point out that these areas, the PFC and the striatum, have been sort of the top players in the key question that we're asking, which is, what are the neural mechanisms behind complex planning? And today, my talk is going to be primarily about our little 2 cents that we're tossing into this specific question. And so to study planning, complex planning, particularly in animals, is very difficult because, as far as I know, most of them don't know how to speak English. Specifically, we designed a task that is typically used to study planning in humans, that is 4 in a row. Now, 4 in a row is a very simple task. The idea is pretty simple. Your goal is to get 4 pieces in a row while preventing your opponent from doing the same. It's essentially a glorified version of tic-tac-toe, if you've ever played tic-tac-toe. So this would be a winning configuration here. And you can do it horizontally, vertically, or diagonally. Pick your favorite. And before I move on, I want to acknowledge Minyoung Park, who is my key collaborator at Johns Hopkins University. She was the one responsible for training the monkey and collecting the data. I'm just the analysis and modeling guy. So she's the real MVP behind all of this. And here's an example of a monkey actually playing the task in real time. So the yellow is the joystick, red is eye movement, and the monkey plays in blue. And you can see sort of successively, the monkey is looking to see if there's enough room. You know, it's always really interesting when I watch this video because I always try to like think in my own head about what exactly is going on, like what exactly is this monkey thinking? And I've spent many hours trying to, you know, wrap my head around the mind of a monkey. So you can see that it's sort of completing its patterns until at the very end, it does indeed get 4 in a row, and then it gets some juice. Cool. So how would we begin to model something like this? We're interested in starting to think about the behavior of this monkey, and particularly in the past, when we've modeled this on humans, we've used something like a tree search, which looks at the next move and then your opponent's next move and so on in this sort of branching tree. For us, we wanted to start with something a little bit more simple, maybe something a little bit more interpretable, and we started with a heuristic model. So we looked at a bunch of different heuristics, specifically distance to the center. This is a 4 in a row feature. 3 in a row double threat, which basically means that there are 2 empty spaces on the side. So if your opponent plays here, you can play here in the next turn, and if your opponent plays here, you can play here in the next turn. So you're guaranteed to win. Connected 3 in a row, disconnected 3 in a row, connected 2 in a row, disconnected 2 in a row, and so on. And then finally, we have some blocking features. So this is blocking your opponent's 4 in a row, and this is blocking your opponent's ability to make 3 in a row. Cool. We all good with that? Great. So our model is fairly simple. We basically take a input state. We ask for every given space in the board that's available, how many features can I create with that space? And then we weight the features according to some learned weights and get a probability distribution at the end of where we think the monkey is going to move. So it's basically a logistic regression on these features. Now, we can compare this with the tree search model, and we can see that they perform similarly. This is across 11,000 games. You can imagine that the monkey has gotten pretty used to this game at this point. But we can see that the heuristic model and the tree search model perform similarly, suggesting that both of them are relatively good at, or relatively similar in their ability to model the monkey's behavior. And indeed, we also have 2 other models, the self-only model, which basically doesn't have any of the opponent's features. So basically no blocking. The model doesn't care about blocking at all. And the simple model, which doesn't differentiate between connected and disconnected 3 in a rows, connected and disconnected 2 in a rows. Those are basically 1 3 in a row feature, 1 2 in a row feature, so on. And we can also lesion any one of the features of this model. And indeed, we see that all of these models perform significantly worse than the heuristic model, which suggests that all of these features are relevant or important to explaining the behavior of the monkey itself. Yeah, so this is just zoomed in so that you can actually see the 95% confidence intervals. And the tagline here is that the heuristic model and the tree search model both best predict monkey moves. But not only that, if we look under the hood, we can see that the heuristic model actually learns a sensible prioritization of these features. So 4 in a row is the heaviest weighted feature, and then 3 in a row, 2 in a row, and so on and so forth. And then we also wanted to look at the eye movements. So one of the things that is clear to us is that, if the monkey is using its eyes to look around the board, it ought to be looking at places that are promising for where it's going to move. And so we wanted to see whether or not the heuristic model could make any out of distribution predictions about the actual gaze patterns of the monkey. So again, we didn't retrain the model at all. This is just a model that's used to predict the behavior. And we saw whether or not it could recapitulate some of the trends in the eye movements. Indeed, it could. And if we look at the cross entropy of this with the other models that I mentioned earlier, we see that the picture has shifted a little bit, but the heuristic model still performs pretty well. And the interesting thing is that the tree search model actually performs the best, which suggests, at least to me, that the tree search model is able to capture something via the eye movements that maybe we weren't able to detect through the behavior, the sparse behavior alone. We also wanted to look at the time scale of eye movements, right? So we wanted to ask, does the monkey's gaze pattern differ for different features that it's completing? So if we have time on the x-axis, and here's where the monkey actually ends up making its move, we can ask the question, what proportion of the time is the monkey actually looking at a given feature? So here, if the monkey has a 4 in a row and it ends up completing it, around a second before the 4 in a row, it actually spends around 80% of its time actually looking at it, right? Maybe not so surprising, but what is surprising is that we see this really nice ordering between 4 in a row, 3 in a row, 2 in a row, and others. And maybe even more surprising than that, that trend completely disappears when the monkey misses this. So for example, this is a curve of when the monkey has a 4 in a row available to make, but doesn't actually end up making it. Cool. So finally, I wanted to talk a little bit about the neural analysis, which is we're just scratching the surface of. We can do a similar plot here where we center around the opponent's move now. So our main question here is, do individual neurons encode opponent features and state values? So if we have the opponent moving at time 0 and we plot the firing rate in hertz, what we can do here is we can plot what happens when the opponent achieves a 4 in a row. Right? So this is the opponent's maximum connection length, which means that the best feature in the board for the opponent right now has four pieces, which means that it's 1 at time 0. So we can see that even though the opponent wins here, about half a second ago, this is an individual neuron in caudate. This individual neuron in caudate has its peak activity around a half second before the opponent actually makes that move. And also, again, we see a really nice graded response for 4 in a row, 3 in a row, 2 in a row, and other. And we see similar responses across all 3 brain areas. So we see something like perhaps maybe the anticipation of the opponent's move, the reaction to the opponent's state, encoding of board state values, and so on and so forth. Now, these are just individual single neuron examples, so I wouldn't extrapolate them to the brain areas themselves. But it is interesting to see that we can indeed sort of see this graded response to the opponent's maximum connection length in individual neurons. And so this is something we want to look into a little bit more later. And how pervasive is this trend, you might ask? Well, one of the things that we can do is for any given time point t, we can ask, is there a significant linear relationship between the max in a row and the firing rate? And if we plot that, we can see that indeed, across time, even around a second before the computer actually makes its move, we have like 15 to 25% neurons that are significantly linearly related to that feature that I mentioned earlier. And this is now across all of the population of neurons that we've collected over time. And I wanted to end with, before I go into takeaways, I wanted to end with this video, which I think, because seeing is believing, here's a video of real-time play with neurons from DNPFC and DLPFC, and you can hear the spiking. And I just wanted to see whether or not you guys can predict what these neurons might be encoding. So here we go. I guess the sound is cut off, but yeah, so there's sort of like a little popcorn noise that happens right around the time when the monkey actually does end up doing the making its 4 in a row, which is pretty neat and something that we actually want to look into a little bit more in the future. And so as far as takeaways go, we trained a monkey to play a game called 4 in a row, which is typically used to study planning in humans. Our model suggests that the monkey pays attention to game relevant features, as well as that's supported by the time movement of eye movements. And then finally, we also see similar trends in DMPFC, DLPFC, and CAUDE with respect to opponents' features. With that, I'd like to thank the members of the Model Lab as well as the Lee Lab, and also thank you for your attention. And if you have additional feedback or questions or just want to nerd and yap about neuro, feel free to send me an email.